Hello, everyone. Welcome back to day 42 of me coding every day. So recently I've been doing the dynamic programming, one-dimensional dynamic programming. Yesterday I did word break, so today we're going to look at longest increasing subsequence. Today is a Wednesday. So I'm thinking maybe tomorrow or later this week I'm going to try doing a day where I just revisit older programming questions just to reinforce that knowledge and kind of go back to it and see if I can solve the ones I didn't. And for this problem with dynamic programming, I'm just going to focus more on kind of like problem solving and just being kind of methodical about how I approach a dynamic programming problem. And I think my goal this time isn't necessarily going to be to solve this problem, but it's going to be to kind of reinforce that dynamic programming way of thinking. So yeah, that's my goal for today. So let's get started. Longest increasing subsequence. Given an integer array nums, return the length of the longest strictly increasing subsequence. A subsequence is a sequence that can be derived from the given sequences by deleting some or no elements without changing relative order. Okay, so cat is a subsequence of crabbed because of C-A-T. So in this case, we removed the R and removed the B, and then we get cat. So we have to figure out for nums, which is the longest strictly increasing subsequence. So if we look at the examples, we have 1, 2. So here the longest subsequence is 1, 2, 3. We can't do 3 because it said strictly increasing, and then 7. So we output the length of that subsequence, which is 4. And then here it's probably, 0, 1, 2, 3, which is 4. Okay, so the problem itself is really easy to understand what it's asking. Okay, so going back to what I was saying earlier about the way of thinking with dynamic programming. So the way that I have seen a lot of people start and the way that helps me visualize a problem is with a decision tree. So let's think about the decisions that we make. So in this case, I think it's either if we keep a number in our subsequence or if we don't. So for instance, we start with empty list and we can either, so let's look at this one, nums equals like that, right? So we can either keep the 9. So here I equals 0. So we can either keep the 9. So going to the left will be keep and going to the right will be skipping it. So that will give us this subproblem, and this will give us empty list. Okay, and then we can repeat this process. So here we have 9, 1. And let's say if we don't keep the 1, it would just be 9. And here would just give us the 1, and here would give us empty list. Okay, and we'll do it one more time. See if I notice any patterns. Okay, so if we do it one more time, the next number is 4, so here would be, well, actually, interestingly enough, so this branch here is actually not valid anymore, because if we, do any combination from this point, 9, 1 is not valid because 9 is greater than 1. So, we could have 9, 1, 2, 3, all the way to infinity, but this subsequence is invalid because it starts with 9. So we can just stop at this branch here. We don't have to continue that one. And what was the other one? 4. So here would be, if we keep the 4, it would be 9, 4, which is also invalid. And then if we don't, it would just be 9. So this one is also invalid for the same reason. Okay, and then if we look at 1, so we can keep the 4, 1, 4. This is valid. Or we can skip the 4 and get 1. And same thing here. We can add the 4 or remove the 4. Like this. Okay, so this is our decision tree. So I'm noticing that we can quickly rule out any sequences any subsequences that aren't increasing. And we could also rule out, so if we get a valid, if we get, so I was thinking like here we got a subsequence of length 2. So I was going to say we could rule out anything that has less than that, but that's not necessarily true. Or is it? No, it's not. Because if we had like 7, 8, 1, 2, 3, we would get 7, 8, which has 2, and then when we first encountered the 1, we need to keep that because the answer is actually 1, 2, 3. Okay, so here's the decision tree. We can either keep it or not. All right, so this is kind of a complicated example. It goes pretty far. But in terms of how we can repeat these problems, maybe we can look at, so I know in coin change with the bottom, I was looking at the bottom up solution of it, and you started from the back and then kept track of the state at that point. So let's kind of look at that. So if we look at 9, 1, 4, 2, 3, 3, 7. So in this example, we know that the answer, if this is the start of the subsequence, equals 1 plus the maximum length subsequence in this region that starts greater than 9. So that's sort of like a subproblem there. So we know that that is 0. There is no, like the maximum subsequence in this region that is, the start point is greater than 9 is 0. Okay, right? So if we could just, have that answer all the time, then we'd be able to solve the problem at every point. So similarly, this is, so like if we take the subsequence at the max length subsequence at this point, it's 1 plus the max subsequence in here that starts at a number that's greater than 1. Which in this case is 3. So that would be our final answer. So maybe at every point we can record. So the problem is, for me, the caveat is it has to start at a certain number to be valid. So like what we could do is just store the maximum subsequence at every position. But the problem then would be you'd have to keep going until you find a number that's greater than. So for instance, I can maybe illustrate this. So we know at 7, so let's start from like the bottom up, I guess. So 7, the max subsequence here, the max length of the subsequence is 1, which is just itself. Okay, then we look at 3, 7. So it's 2, because it's, we can define this as 3 plus the max subsequence here that starts greater than 3. So maybe we can store, okay, if you are less than 7, then at this point it's 1. Otherwise, if you are greater than or equal to 7, at this point it would be 0. Maybe we can store this information. So for instance, if this was 8, we would fall under this bucket. So it would be 1 plus 0 equals 1. Okay, but because here it is 2, because we fall under this category. So it's 1 plus the max subsequence here that is greater than 7. So now it's 2 here. And now we have more information to add. So if you are less than 3, then you can get 2. If you are greater than or equal to 3, then you can only get 1 from this. And then can we delete this information? I don't know. Let's see. Let's see if we ever reference this part again. Okay. So next, here is 3. So we look at our current memory here, I guess. So 3 is greater than or equal to 3, so we can only get 1 subsequence. So this would be 1 plus, the max here, which we've defined as 1 in this bucket, so this would be 2. Okay, so now, and then this would create the same table. Okay, so now if we look at 2, so we look at our memory, so it's 1 plus 2 is less than 3, so it's 1 plus 2, which is 3. And now we create a new thing to remember in memory. So this is interesting. So if we're less than 2, then it is, if we're less than 2, we can get 3. If we're greater than or equal to 2, then what do we get? I guess it would be, I'm noticing that this number here is always 1 minus, like it's always, like B is always A minus 1. So I don't know, so should this just be 2? In this case, it's true. So let's pay attention to this and see if this holds true. Okay, so next, we're at 4. Okay, so if we look at our memory, 4 is, okay, so this is interesting. So 4 is greater than or equal to 2. So according to our current method, it should be 3 at this point because we see greater than or equal to 2. So this would tell us that it's 3, but this is incorrect. The answer is actually only 2 here. So why is that? Well, we kind of use this part. So it's almost like we have kind of like we're separating it into buckets almost. So if it's like, if we have a line, right? So we have 2, 3, and 7. And we're saying, then after that as well. So we're saying if you're greater than 7, you get 0 points. If you're between 3 and 7, so you're less than 7, you're greater than 3, then you get 1. If you are between 2 and 3, you get 2. Well, there's no number between 2 and 3. Okay, so if you're less than 2, then you get 3. So if you are 2 or you are 3, at this current state would give you, okay, so instead of doing this, let's retry it with the number line sort of thing. Okay, because that proved not to work. Okay, so here 7 is 1. So now there's 2 states. If you're greater than or less than 7. If you're greater than 7, you get 0. If you're less than, you get 1. Okay, and now 3. So 3 is less than 7. So we add a 2 here like that. 3, same thing. We don't have to update it. Okay, 2 is less than 3. So it gets 1 plus 2. And that gives us, so 2 is here. And then if you're less than that, you get a 3. Okay, 4. So if we look at where 4 fits in, so 4 fits in this bucket here. So that means 4 gives us 2. So if we expand our horizons, so 4 is here. So now if you are here would be 2, I believe. So if you're less than 4, then you would get 2. But you're greater than 3, which with integers is not possible, but theoretically I think this is how it would work. Okay, now 1. So 1 is less than 2. So we get this number, so it's 1 plus this number. So that would be 4. And then 9 is greater than 7. So you'd put it here and change this number to 1. So this only tells us at, like, so if we were to get a new number, it would tell us, like, based on what range you're in, you can pick it here. So let's say our next number was, let's say 5. We would say, okay, the maximum subsequence at 5 at this position would be 1 plus, and then the number at whatever bucket 5 is at. So 1, so 2. So if we had a 5 here, it would, yeah, that makes sense. So we can kind of use this. All right, so I think this makes sense. And then we can just return the max out of everything that we found. Okay, so what this needs, so now the question is, how do we represent this in a data structure? And the question is, yeah, I guess that, so to determine the answer to how we represent this as a data structure, we need, so we need to know, like, given a number and, like, so this kind of reminds me of, like, maybe we could use, so if you think about it, okay, so obviously if we just did like a linear scan here. So let's say we had, let's say we had a dictionary where each element mapped to, if you are less than this number, how much do you get? Okay, so 4 would be 2, 7 would be 1, and 9 would be 1 as well. So this dictionary tells us if you are less than this number, your substring is 1 plus whatever its value is, right? So now the question is, how do we efficiently find the number that we are most directly less than? So let's say our input number is 6. How do I find, given 1, 2, 3, 4, 7, 9, so basically just like an unknown array, how do I find which number this is most less than? And to me, it kind of sounds like you can binary search it. So you can binary search it, I believe, because you could say, okay, 6, start in the middle, and then you can kind of like, because we know this will always be sorted. It will always be sorted, or maybe that's just the way I drew it. Could just be the way I drew it. Okay, so now I'm going to make a statement. So if our sort of timeline here is sorted, then we can binary search to figure out where it should go, and then just do constant lookup. And that would just be log n. Okay, so now I'm going to repeat this and pay attention to how we could implement that. So if we had an array of our, if we had a sorted array of our keys and we had this dictionary, then I would know how to solve it. Okay, so we have 7, and then we say 0, 1 like this. I guess what we would say is, so we would have, okay, so our array would start out with just infinity, and then we would insert 7 into it, so then it would become 7 infinity, like that. And then in our dictionary, we would say 7, 1. Okay, and now 3. So we binary search 3 to see where it goes. So we binary search 3 to see where it goes. Then we determine it goes here. And now we say, well, okay, so it goes here, so check the number after it. And then also we say infinity 0. So now check the number after it and do 1 plus that number. So then, and then add that to the dictionary. So 3, 2. And then, okay, so this part's a little tricky because we have to insert an element into our array, which is n. Okay, so let's say this is n, right? So n times we are going to binary search and then insert. Does it give me a recommended time complexity or no? No, it doesn't. Is there a better way to do it besides inserting? I don't know. Okay, so I think this solution is n squared, which, what's our input size? 1,000, so n squared is fine. Okay, so I guess I could try implementing this, and then for duplicates, I don't necessarily know what to do either. So we would binary search it, and then I guess what we would do is just have to place it on the right. So like we would insert the second 3 here, like this. And then it would reference this one, and it would say, okay, and instead of 7 to 1 and 3 to 1, here we would actually want their index. So if we index these 0, 1, 2, then we would say index 6. Okay, so the duplicates is adding some complexity. So we'd have to store maybe each of these as tuples, where it would be like the value and then its index. So maybe you could binary search with the value in the tuple, but then once you get it, you look up the dictionary, this specific index, because we need all of these to be unique. Because if you have, for instance, the number list 3, 1, or does it even matter at all? Yeah, it does matter. So if you have 3, 4, 3, okay, this has a maximum of 2, and this has a maximum of 1. So we can't just store the value because it matters on the position. Because if we had, let's say, a 1 here, and maybe, I don't know if we could do this in reverse, but I was thinking somehow if we calculated this first, then we would say 1 plus 2 from this 3, even though this 3 only has 1. But I don't know if that's actually possible. Because in theory, every duplicate that we find after, so if we're going right to left, every duplicate that we find should have, it can't get worse. Like, it could only get better. It could only get better. So here, this one is 1, and this one is 2. If you have, let's say your whole nums array is just 3s, then they're all going to be 1. So I wonder if we can just like overwrite this and just say that, hey, when we encounter this 3 now, if you're less than 3, it's this one, and we don't care about this one. I think that might work. So maybe we can actually store these values after all. Yeah, okay, so this looks kind of fine. So I guess we'll go through backwards. Okay, so let's kind of think about this here. So we're going to go through backwards for I in range length of nums. So we're going to start at length of nums minus 1, go until minus 1, and go backwards. So if I print nums of I here, this will give me all the numbers in reverse order. 7, 3, 3. Yeah, perfect. Okay. So I want this. So let's assume for now we can use the values. Okay, so then if we have, what could I call this? So this would be, I guess, memo. And this is like the order. Sort of like, where do you fit? Is there a better way to do this than inserting and binary searching? I don't know. Is there a data structure where I can add a 7, add a 3, add a 3, add a 2, add a 4? To me, it seems like you could just maybe just insert it like normally without binary searching. Maybe I could start with that, because that would just be, well, that would be n cubed, I guess. Because for each element, you add it to this list and then insert it. Is there a better way to do this? All right, okay, so right now let me just try the n cubed solution before I start over optimizing. So what I'm gonna do is insert it. I want to insert each value into here and then take the values after it. Okay, so we'll have, I'll call it like order. Then I'm going to define an insert function, which takes a value and a list. Then we say while value is greater than or equal to, in this case, a list of I plus equals 1. You will say I equals 0. And then we will say a list dot insert value at position I. Okay. All right, so what I want to do is, so I want to take this number. I would like to insert that number. So insert nums of I into order. So order also, I want to have one element, which is infinity. So nothing should ever be bigger than infinity. Okay. And then, so let me just insert all of them into order and then print. Let me print order at every step here. So if I print f order equals like this, let's try that. Okay, 7 infinity, 3 7 infinity, 3 3 7 infinity, 2 3 3 7 infinity. Okay, so it looks good here. So now we're going to take all right, so then, and let's say, still not muted. All right, so we'll have infinity will map to 0. Okay, and now we're going to say that memo of, so how do we get its, maybe here we could return I. So it'll insert it and then give us the position it was inserted at. So let me print position here. Okay, let me be more specific. Inserted what did we insert? Nums of I into order at position. Let's see if this is what we want. So we inserted it to position 0, position 0, position 1, position 2. Okay, looks good. So we want to take order of position plus 1. So we want to say 1 plus, so this is the max substring we can get at this point. And we want to say memo of me, so nums of I, equals 1 plus order. So I'll keep this for now, and let me just print memo at every step. So here, okay, 7 is infinity. All right, so we want, okay, so we actually want memo of this number there. Still not muted. Okay, so infinity is 0, 7 is 1, 3 is 2, 3 is 2. 2 is 3, 4 is 2, 9 is 1. Okay, and then we just want to keep track of the max total value. So we'll say result equals it's negative infinity, or I guess I can say 1. And then we'll say result equals max of itself and that. Okay, and then if I return result, does that work? Okay, that does work. Let's see if I get TLE. I got something wrong. Wrong answer. Okay, I was not expecting that. I was expecting TLE. My output is 5. But it should be 6. Okay, so 1, 2, 3, 4, 5, 6. So at 10, it's 1. At 9, it's 2. At 7, it's 3. At 6, it's 4. At 3, it is 4 also. Is it because we have duplicate 6s, perhaps? Let's see. Whoops, should have saved the test case. Rate limit exceeded. Okay. Okay, so here, the problem is here. So when we insert 3, its value is only 4. So why is that? So it's getting... So it's sorted. So 4... Oh, okay. So maybe this isn't working. Because this 4... Okay, so I don't think my solution works at all. Because this 4 has basically a score of 3, but this 6 has a score of 4. So we should obviously pick the closest number. So it's doing 3 plus the highest in this subproblem, which should actually be 4. Okay, so I think I just have to rethink it slightly. So let's go back to the drawing board. So here we have 1, 3, 6, 9, 4, 10, 5, 6. So when we get to this 3, it should be 1 plus the max in here, which the max in here is 1, 2, 3. So it should be 1 plus 3. Okay, well, I'm a little confused because 4, 5, 6 should, that's also 3. So why is it not 4? Or it is 4. So wait, is this correct? This is 4. 2, 3. We also have 1, 2, 3. Wait, why is this 6? Expected output 6. 1, 2, 3. Or is it 1, 2, 3, 4, 5? 1, 2, 3, 4. 1, 2, 3, 4, 5. The output's 6. Did I miss a number? I missed a number. Okay, that's why. So it's 6, 7. Like so. Okay. Okay, so we know here it's a 1. So let's see what's right. So here it's 1. Here it says 2. It says 10 is 1. That's correct. It says 4 is 3. That's correct. 9 is 2. That's correct. 7, it says 3. 7, 9, 10. That's correct. 6, it is 4. So that is correct. 3, it's saying 4, but it should be 5, right? That's the problem. Okay. So the way my algorithm works now is it checks the next most recent high number. So it's checking 4 and it's saying, okay, 1 plus 3, that's 4. But what my algorithm is not taking into consideration is that there could be a higher number, like 6. The 6 is greater than 4, but it has 4. It has 4. So we need to keep track of the max seen so far at this index. If it's greater than because, for instance, if this was like if we had 10, 2, 3, 4, if we had 10, 2, 3, 4, it's not 1 plus the max in here. This one only works because 6 is bigger than 3. So here we have several options available to us as 3. We can pick this one. Let me think of a different color. Let's try purple. So we could pick this one. Or we could pick this one. Okay, now this is problematic because we could have like 1,000 and then we could have 1, 2, 3, or I guess we could have like 10, 9, 10, 11, 12, 7, 8, 9, 4, 5, 6, and then this 1,000, or not, I guess it wouldn't be like 3. Let's say it was 3 here. So in this test case, this 3 would have to check 10, like this sequence, 7, the sequence, and 4, the sequence. So it could do that a lot. So I wonder if we have to divide it into like valid sequences, or if there's just some way for us to know. Because with coin change, for instance, no matter what the value is, you have like a solution at that point. Like, so here, like it's weird because the solution is, the max substring here is, or subsequence is 2, unless you're greater than 5. So it's like that duality of it that's kind of tricking me a bit. And then when you add another one, it's tricky because now it's like, there's all these states where it's like, there's 3 different answers depending on your value relative to these states. So if you're between 5 and 10, then you'll get 1 from this. If you're less than 5, you'll get 2. If you're greater than 10, you'll get 0. So now it's like we have to keep track of this many states. And sometimes you'll have several options. So for instance, like in the case of 3, it's 3, 4, 5, 6, 7, 9, 10. So at 4, there was 3. So if you were less than 4, you had 3 available to you. If you were less than 5, you had 2. If you were less than 6, you had 1. If you were less than 7, so this is where it's weird. If you're less than 7, you have 2 available to you. Well, there's also 2 6s as well. So let's say that 6 was the higher one. Then you would have 3 available to you here. Well, actually, this 6, you'd have 4 available to you. So if you're less than 7, you would have 3, because I forgot the 10, 7, 8, 9, 10. Or 7, 9, 10. Okay, so less than 4, you would have 3. These 3. Less than 5, you would have these 2. Sorry about that. Less than 6, you would have these 4. Less than 9, you'd have these 2. And less than 10, you'd have this 1. And then after that, you'd have 0. So it's like we have to keep track of all these states, but not only that, you can't just check the state in front of you. You have to know. So maybe we could store like the max here. So we know at this point what we can simplify. What can we simplify this to? Like if you're between 4 and 5, you're never going to pick 2 because you could just pick 4. So can we simplify it to this? If you're less than 6, you get 4. If you are less than 7, so this one matters. So if you're less than 7, you get 3. If you're less than 9, you get 2. And if you're less than 10, you get 1. So all that is relevant. But none of these are relevant. So if it's ever decreasing, then you don't really care. What I mean by that is like, so here it's increasing. So like 0, 1, 2, 3. That is all relevant. But here when you go 4 and then jump down to 2 and then back up to 3, that doesn't really matter. So I don't know how I could store that. Because if we had, so if we did this problem, but we had access to this array, then we could solve it the way that I'm doing. So how do we get it to be this? How do we get it to be that? So I think it's some trick where like you don't add things. So here with 6, it's, this is relevant. If you're less than 6, you're 1, otherwise 0. Now we add 5. Still relevant. Still relevant like that. And now 10. So 10 goes here. So now this becomes 1. And this becomes 0. So now this doesn't really matter anymore. It doesn't matter if you're above or below 6 anymore. It just matters if you're below 10. Right? Yeah, because if you're above 6 but less than 10, it doesn't really mean anything. It's still the same as just being less than 10. So we can simplify it. Okay, so then we look at 4. Now 4 does matter. 4 goes here, and now it's 3. And now we look at 9. So 9 tells us if you're less than 9, you have access. So if you are less than 9, if you're less than 9, you have access to 2. You have access to 2. So now that tells us we don't really care about your relationship with 5. If you're between 4 and 9, it's going to be 2 no matter what. So what if you're 7? Then yeah, it would be 9, 10. If you're 4, then it's still 5, 6. So we can simplify it and just get rid of this and put it to 2. I don't know if this is making sense, but what I'm noticing is we don't have any repeated numbers. Okay, so that was 9. So now we look at 7. So we see 7 goes here. So 7 would be 3. So 7 is here. That's a 3 and that's a 2. So now we don't care. This is a 3, remember? So we actually don't care if you're less than 4 or if you're less than 7. It's going to be 3 no matter what. It's going to be 3 no matter what, because if you're 6, right, then you get 7, 9, 10. If you're 1, you could do that, or you could do 4, 5, 6. So it doesn't matter. Okay, and now 6 comes along. 6 is less than 7. So it gives us 4. Now it tells us 3 comes along. Okay, so with this new and improved idea where each, like there only exists one, so each has a range. So 1 has a range, 2 has a range, 3 has a range, and 4 has a range. Now it would work when we get 3, because 3 would be in this range, and then it would say that's 5. And then, okay. So I'm noticing 2 things. So either you are like left of number line or you're not. So if you're not, then we delete something. Let me try again with that in mind. Sorry if this is taking a while, but this is helping me. So 6. So right now we only have one thing in our number line, infinity. Which is 0. That's in our number line. So we have infinity mapped to 0, and we have infinity. So we're less than infinity. So because of that, we've achieved a new maximum length. And now we say 6 is 1, and then we put a 6 here in our list. Okay. Now we look at 5. So 5 is less than, so we add it to the left, and we do that. And same thing. So 5 is 2. Now we add 5 here. Okay. 10. So 10 does not add, it's not the leftmost element. So if it's not the leftmost element, then surely we're going to delete something because we'll have repetition. So 10 would slot in here, and this would become 1. So if 10's here, then what that means is we basically just replace 6 with 10. Okay, so replace next lowest number. So is that what happens? So because 10 is, 6 is the next lowest from 10. So we basically just increase the range from 5 to 6 to now it's 5 to 10. So if you're within that range, you'll get 1. Okay, now 4 is the next lowest. So we just do that. 9. So do we just replace 5 because it's the next lowest? Using that hypothesis, let's see if that's true. Yeah, okay, it looks true. So if you're less than 9, but you're greater than 4, so 7, then yeah, 9, 10. Okay, 7. This doesn't, it's not a new one, so we just put 7 here, like that. Okay, 6. 6 is new. 3 is new. 1 is new. I think that's it. So the key is, are we the next lowest or are we not? Okay, so if we're the next lowest, so this is all good. So if we're the next lowest, so there's either if position equals 0 or if it doesn't. So if it does equal 0, then we do this. Same, what we wanted to do, right? And we don't really need to keep track of the result anymore. We can just return our most recent thing that we've added. I don't know. So when we add 1, right? It's 1 is equal to so memo of nums of I equals 1 plus position plus 1. Yeah. And then, okay, so order, we don't actually want to insert the element. What we want to do is replace the element. So let's say, yeah, we'll do insert. So we can say same thing, right? But instead of doing this, we'll say if I equals 0. So if it's the least element, then we'll just insert it at position 0. Otherwise, if it's not, what we want to do is say a list of I equals value. Okay, so let's try that. So what I'm gonna do is, before we do that, I just want to print I want to print order every time. So see if that works. So let's run that. Should probably ignore this. Okay, let's run that. Okay, what's the problem? While value is the list empty somehow? What's order? No, it has something. Okay. Insert 7, inserts 3. 3 replace. Okay, I forgot about the duplicates. Let's get rid of that. Just have the duplicates be the same. The duplicates are kind of messing things up. Okay, let's look at this one. So 6 gets added, 5 gets added, 10. So it deletes infinity. Okay. So if it's at the end, it's also, if it's at the end, then it's also tripling. So like 10, for instance, inserts here. So it's bigger than this, so I is 1. It's bigger than this, I is 2, and then it replaces that. Is there an elegant way of doing this? So we want it to replace it unless it's infinity. Let's say this. If I equals 0 or I equals length of a list minus 1, then we'll just insert it, add that element. Otherwise, we'll replace the element. Okay, I thought I was muted for a second. So case 3, 10 infinity, we insert 4. Now we insert 9. So 9 should replace 6, right? All right, let me do it again. Just see what it should be. So 6. So first of all, infinity to 0. 6 goes here. 5 goes here. 10 should replace 6. Okay, so maybe we just want to say like that. Five, 6, 5, 10 infinity, 4, 5. So 4 is less than 9 is, where does 9 go? 9 should replace 5. 4, 9. Okay, and then we end up with 1, 3, 6, 7, 9, 10. Okay. Okay, perfect. And this is a little, I wonder if I could reverse it to make it so we can append to the end or something like that. Because inserting to the beginning is, for now, I'm just going to import deck. There might be a way to do it without that. And then here I'll just say append left. That should be the same. All right. 1, 3, 6, 7, 9, 10. Okay. Sweet. So what do we want to do? We want to get, so we insert it and then we say, I think this is what we say. So memo of this one equals, well, we only want to do this. Maybe we should just put this here. Okay. So I'm thinking we'll set j and we'll insert it. So if j is 0, then we want to do this. So it just equals 1 plus the previous one. Otherwise, we'll say memo of nums of I equals memo of nums of I equals memo of a list. Instead of a list, we want order. So this one equals what it's going to replace. So order of j minus 1. So set my memo, and these i's should be j instead. Except maybe this one should be I. And then we can delete memo of Alright, let's see if we get any errors there. Val. So what's val? Val is nums of I. Position is j. Is this supposed to be J? This should be J also. Okay, this kind of messed me up, to be honest. Okay, so it's supposed to be going backwards. So it starts out as infinity, and then it should add. All right, this I and J stuff kind of messed me up, to be honest. I'm just gonna undo it. Okay. Okay, so 1, 3, 6, 7, 9, 10. Okay, that's where we were. So I'm trying to optimize too early again. Okay, so we'll say if position equals 0, then we want to set this. Otherwise, memo of nums of I equals 1. No, it just equals whatever. So memo of order of position. So for instance, all right, let me print that and let me print memo. See if this looks right or not. So 6 is 1, then we add 5, 5 is 2. So what's something that replaces? So 10, it says 0. But I want 10 to be, so 10 replace 6, so it should do 6. So let me print. Let me print this. Position equals 2. Okay, so it should be position minus 1 then. 4 doesn't exist. But so we print it and then it says 10 equals 0 because position. Okay, so we have to do it. So we replace it, but we had to store this value. So can I do it here? Can I say memo of value equals memo of a list? Can I do that? So now 10 is 1. Okay, so 5, 6, 10 is 1, that's good. 6 should be deleted, but that's okay, I guess. 4, 5, 10. So 9 replaces 5. So 5 was 2, so 9 should be 2. Okay. And then I just also want to delete memo of a list of I minus 1. Like that. Okay. Okay, so Okay. So 10 got deleted. So 10 is not in the memo anymore. So it doesn't look like that did anything. So when I take out the delete, does it work? Okay, when I take out the delete, it works. 10 is 1. Okay, so if we look at it at the end, infinity is 0, 10 is 1, 9 is 2, 7 is 3, 6 is 4, 3 is 5, and 1 is 6. So there's definitely a better way of doing that. Okay, so this one has duplicates. So what do I need to do about duplicates? So I'm thinking if it's equal to, okay, yeah, then it would just replace the old one. Okay. So I got the problem, but yeah, it's getting pretty late. This is just so messy. I wish I could delete it. I just want to remove this key from the dictionary. Can I say like memo dot remove from like, to remove a key from a dictionary? I thought it was the delete keyword. But this doesn't, this ruins it for some reason. Also, I wish I could just return, so I could return I, and then I want to figure out the most recent one that we inserted. But I guess we can do it by doing this. Yeah, this is super weird. Let me see if it works on LeetCode. So this is longest increasing subsequence. Because a lot of times I'm finding on LeetCode, it doesn't actually work on LeetCode. yeah, for instance, this one. Wait, do I have the delete in still? Wait, does it not work anymore? Oh, what did I do? Is it this? Okay, so it got past the run, so let me try submitting it. Okay, I literally have no idea how this is a good solution. I mean, I guess it makes sense. I just feel like the solution itself that I have is not bad. I think I'm just, have a lot of fluff here, and I could optimize it a lot, but I'm pretty tired, and it's been an hour and 15 minutes. So yeah, I'll just call it for today's episode. This will be one of them that I'll revise. Um, yeah, it's just kind of sloppy code. I think the idea is kind of correct. But anyway, thanks for watching, everyone. See you guys tomorrow for day 43.